Problem number 23. An imperfect spring has a restoring force F that depends on the displacement x from equilibrium as in the graph shown below. The slope of the curve for x less than negative d and x greater than d is a constant k. A mass m is attached to the spring and released from rest at the position x equal a, where a greater than d. What is the period of the subsequent motion? Solution for problem number 23. On this graph we can see that motion from point D to point A is perfectly harmonic motion, same as from negative D to negative A. It means that we can count what is the period of this motion, except motion with a constant speed between negative D and D. That will be t1 equal 2 pi multiplied by square root from m over k. Now let's count what is the speed of this mass during motion from negative d to d and back. That we can count from energy conservation. And from here v equal square root from k over m multiplied by a minus d. And now we can count what is time to move object from negative d to d and back from d to negative d. That will be 4d over v, or this expression. And finally total time equal t1 plus t2, or this expression, which is answer C, and that was a solution for problem number 23. Problem number 24. Two satellites are in circular orbits around a star with equal radius r, speed v and a period t. The satellites are initially diametrically opposite each other. In order to meet the second satellite in time t over 2, the first satellite should decrease its speed to approximately next one. Solution for problem number 24. First, let's use third Kepler law to count what is the size of a semi-major axis for second satellite. We have this relation, that cubes of a semi-major axis equal to squares of periods, which in our case 1 over 4. It means that for the second satellite, semi-major axis equal this expression. Now let's use equations for total energy. For the first satellite we have total energy equal negative g m over 2r. And for second satellite, total energy equal negative g m over 2a. Now let's count what is energy difference. E1 minus E2 equal this expression, or because in initial points potential energies are equal, that will be difference in kinetic energies. Also we can use expression for circular orbit, that v square equal g multiplied by m over r. Now we can put this expression to this expression and find a relation between v and v2. From here we can find that v2 square equal approximately 0.41 v square, or v2 equal approximately 0.64 v, which is answer B, and that was solution for problem number 24. Problem number 25. Displacement Fred's trusty pellet sprayer is held at rest a distance h away from the center of a planet orb, which has radius big R much less than h. The pellet sprayer ejects the pellets radially outward, uniformly in the plane of the page. These pellets are all launched with the same speed v, so that a pellet launched directly away from orbit by the pellet sprayer can just barely escape it. What fraction of the pellets eventually lands on orb? Hint: you may use the small angle approximation sin theta approximately equal theta for theta much less than 1, where theta is in radians. On left picture we have the pellet sprayer relative to orb, and on the right picture we have a close-up of the pellet sprayer. Solution for problem number 25. Because all pellets are launched at the escape velocity, the speed of one of these pellets at distance small r away from orb is square root from 2gm over small r. At a distance r minimum of closest approach, the pellet's velocity must be perpendicular to its displacement from the planet's center. Then, by conservation of angular momentum for a pellet of mass m launched at angle theta from the vertical, we have mv h sin theta maximum equal mv in point big R multiplied by big R. The pellet collides with the planet whenever r minimum less than big R. Then our equation for theta maximum is this one for small theta. From here we can find that theta maximum equal square root from big R over h, and the range of collisions angle is thus between negative theta maximum and the positive theta maximum, and the range of all of it angles is 2 pi, so the fraction is 2 theta maximum over 2 pi, which is 1 over pi multiplied by square root from big R over h. This is the answer E, and that was solution for problem number 25.